Okay, so we are going to talk about the definition of congruent segments. This is going to be another justification that we are going to introduce into our proofs that we will use when talking about segments. So when we have congruent segments, maybe we have something like segment AB is congruent with segment CD. And remember, when we are dealing with segments that are congruent, our segments get a hat and the congruent symbol gets a hat. So they both need to get hats. Our segments have a little straight hat to look like a little miniature line segment, and the congruent symbol is an equal sign with a little squiggle on top. So we call that its hat. Now, the definition of congruent segments helps us talk about or transition to talking about two things. Segment AB is a thing and segment CD is a thing, and those being congruent to each other, and change the conversation into the measures of those segments. And remember, when we write the measures of segments, it's just AB is equal to CD. Those two segments are equal to each other because their measures are equal. Measures are equal. I can't write. There we go. And two things are congruent. There we go. Now, the definition of congruent segments allows us to transition from two congruent things to two segments whose measures are equal. Lets us transition back and forth between the two while we are doing a proof. That is the definition of congruent segments. And we can look at how that occurs. So we have a provided situation here, and my previous problem is taking over my screen. That's okay. I'll write a little differently. So we have our first statement. We have the situation that says given segment CD is congruent to segment EF. So I have these two congruent objects. It also provides me with the information that CD is equal to 3y minus 9 and that EF is equal to 15. So since that's all provided for me, my justification is given. So from here, I personally, again, like to draw a picture, give myself all of the information. So that's a little large. I have CD and EF. And since they told me that they're congruent, here in our given information, I can mark them as congruent to each other. It also tells me that CD is 3y minus 9 and that EF is a total of 15. So now, because I know these two objects are congruent to each other, because of the definition of congruent segments that we just talked about, I can now transition to saying their measures, so CD without the bar on top, is equal to EF. I do not have a squiggly line on my equal sign, so CD and EF do not get a little hat. They are just letters. And because of the definition, and you can write DEF of congruent segments. The definition of congruent segments lets me say that. Now that I have segment CD and segment EF, the measures of those two segments in kind of an equation format, I can take the information about their lengths, that 3y minus 9 and the 15, and add that into my equation. So when we do that, we have 3y minus 9 is going in the place of CD. And EF is getting replaced with 15. Okay. So now that we've replaced those things, so we have 3y minus 9 equals 15. We are going to now try to solve and get y by itself. Our given proof says y equals 8. So that's what we are trying to get to. So I am going to try to keep y on the left-hand side and move this 9 by addition. So 3y equals 9 plus 15 is 24, and that's addition property. And then 5, we take and divide 3 from y and 3 from 24, and get y equals 8. And that's division property. So now we have our matching statement to our matching proof. They look exactly the same. This took 5 steps. If you took a little bit more, you might want to double check yourself. This one's pretty straightforward. There's not a lot of different ways to deviate. So that is using the definition of congruent segments in a proof. It lets us bounce between the segments are congruent and the segments are equal to each other. And we can use that in the other direction. If we know the two segments are equal to each other, their measures, we can say that the two segments are congruent.